All right. Hi, I'm Joe Schools. I'm a postdoc at JPL and I work with Sue. Today I'm going to show some new models of corona formation that we've been working on. So already today we've been over corona, but just a little bit over again. Everyone's favorite word for corona, they are quasi-circular surface features. Generally, they're defined by an annulus of surface fractures. These nice lineations on the around the circle here in the radar image, generally 100 to 1,000 kilometers in diameter. And they can have complex interiors, including any combination of things like volcanic domes, discontinuous topographic ridges, important for this work, extensive lava flows, giant radiating dike swarms that can go for hundreds of kilometers away. And they're seemingly plentiful on Venus. There's over 500 of them at least. But seemingly none on the Earth or any other planetary body, although I think there are some people in this room that might disagree with that statement. This is from Sue's science paper that shows schematically various topographic profiles that have been observed for corona. And these hatches are where fractures are recorded to occur on these topographic profiles. So ideally, any model of corona formation should be able to somewhat replicate this. Most models of corona formation are imagined as some kind of uplift followed by a collapse. So the sort of general idea is that you have some kind of upwelling, like a plume or a diapir. Maybe it melts, but it uplifts the surface a little bit, and then at some point it collapses and creates the topography and the ridges. And you can also do essentially the same thing if instead you delaminate the lithosphere. So you have material fall off, upwelling mantle fills in, creates topography. And generally these things are modeled as sort of tectonic processes or like purely viscous processes. And we don't really look at the magmatic processes, despite the fact that many of them have clear volcanic evidence at the surface. So that's one thing I want to do. Excuse me. I realize I can't do this talk in less than 20 minutes, so I'm gonna have to skip over. So yeah, existing models focus on tectonic processes, few focus on magmatic models. So what I want to do is to create a model of corona formation integrating tectonic and magmatic processes. And then eventually be able to use model output and spacecraft data to constrain the interior structure and dynamics of Venus. So in order to do that, I am using a finite element model. Specifically, I'm using the aspect package. There's a bunch of benefits to using this, but specifically for this work, the most important part is that there is a melt migration extension. And so what that allows us to do is solve a system of equations describing the behavior of silicate melt, percolating through and interacting with a viscously deforming host rock for things like velocity, pressure, temperature, porosity. So essentially what that's doing, this is an X-ray tomography. I don't think that's the right word. Anyway, this is an image of a hand sample, the inside of a hand sample, showing melt distribution. So for example, in this upper corner here, this is about 1% melt. And so these gray tubules are the melt, and then the empty space, that white space, is actual rock grains. So this is what 1% melt looks like in an actual rock moving through around these grains. And as you add, or as you create more melt, melt the host rock, more and more melt fills in and surrounds these grains. So aspect is essentially approximating this and then doing it on a macroscopic scale. So what we want to do is we want to take this existing melt migration and we want to add in viscoplastic deformation. So we want to be able to break things brittly. I'm not going to go into these equations too much, but I do want to point out, so we're using we're starting with a base of a rheological flow laws. So we have a crust of some flow law and a mantle of some flow law. And then using those parameters, we can fill in these equations. And I want to specifically point out, especially here in this dislocation of viscosity, it is strain rate dependent, and that is going to play into our results. And then from there, we take that, and then this phi here is the porosity. So we factor in the porosity into the viscosity and how that affects it. And then we are able to simulate a brittle deformation by having a yield strength. So if the stress surpasses the yield stress, then it will crack. And then we will go to a lower calculated viscosity. And that's how we're simulating the cracking. Since we are dealing with melt, you have to think about things also volumetrically and in terms of pressures. So you have to actually calculate a second viscosity known as the compaction viscosity. And in that case, essentially very similar. When a pressure reaches, or pressure essentially in the melt reaches a certain yield pressure, cracking occurs, you go to a lower compaction viscosity. So here's our model setup. So going from the outside in. So at the top here, we have a surface with mesh deformation. So we can actually record the topography as the model progresses. We have an imposed surface pressure. On the side here, we actually pull material out in order to simulate a strain rate in the lithosphere, or a set strain rate. And then from the bottom, we have material flow in for mass balance. And then on the inside, we have I call it a plume, not technically correct. It's more or less a diapir, but it's a geodynamic interpretation anyway. So it has some temperature, some radius, and then that will be let go and allowed to rise up into some thermal lithosphere of some thickness and some crust of some thickness that has a separate density and flow law relative to the rest. And over on the left here, you can see the initial resolution. So very, very fine at the surface, so we can record topography, 500-meter resolution. And then this is allowed to evolve over time. So as this ball rises up, it'll resolve up where it needs to and unresolved down below. So going in to show an example of one of the results. So we have this body of set temperature, in this case 1788 Kelvin, a plume of some 130 kilometer radius, 45 kilometer thick lithosphere, 30 kilometer thick crust. And on the left, we're showing viscosity. On the right, we're showing temperature. And then contour lines will appear on the temperature field that show where melt is developing. So initially, it starts to rise up. I want to pause it for a second. Something interesting happens in that expected. So I showed before that the viscosity is dependent on the strain rate. So as this material rises up, it's displacing the material above it, it's flowing inside, and then just sort of doing the whole balance, it comes down, material fills in, so you get this nice flow field going around. That flow field in turn reduces the viscosity and actually makes that the path of least resistance. So instead of rising directly up, it actually preferentially flows out to the sides. So you form this region of low viscosity, but also this viscous cap. Melting occurs, melt rises up, melt actually supports topography of the surface. And then you can start getting these smaller wavelength features where this is high temperature, high porosity, wants to rise up, low temperature, essentially all solid wants to come down, and you can get material interchanges that way. Just a few snapshots so you can see initially 200,000 years, you get a nice little dome in the topography. 300,000 years starts to spread, deflect, melt, good support topography on the side. You form something that's more like a plateau. Further spreads laterally, further melts, more topography. You can support some kind of ridge of about 1,000 kilometers in this case, but after 350,000 years under these conditions. And again, in essentially the last time step of this model, after 400,000 years, you can have 2 kilometers of ridge. So I'm going to go ahead and zoom up here. So this is just also is these surface cracks. So you can report in the viscosity field, zoom in case you can't see. So you could actually see this hatch pattern where fracturing is occurring in the surface. And so I'm using these triangles, and now I'm putting it on the topographic profiles. So in between on each of these is where the fractures form, and then you can directly compare to the schematics and see for our ridges, it works. They're in the right place. Interestingly, for the domes and the plateaus, they sort of tend to be more in the center. Working on that, trying to think about why that might be. Could be, post alteration processes, something. But the ridges work well. So that model terminated. Essentially, these are just very, very high resolution models that I'm running now. They're work in progress. So I have a few lower resolution models to sort of, start to interpret where things might go. So again, this is the same conditions, rises up, spreads laterally, starts to melt. And then interestingly, you can actually start to delaminate that viscous cap that was there before. That comes down, melt goes up, can support topography, and then sort of eventually the melt just sort of breaks through and this enters into a space that this model is not really calibrated for. You're going to have some sort of volcanic processes that are going to take over. And you can start looking at the topography. Like I said, this is a lower resolution model, so we're looking at a few kilometers at the surface of mesh, not 500 meters. And so you could actually see in this case, we get a nice central dome, which we see in corona, actual corona. And interestingly, that central dome develops after the outer ridges, which is sort of an unexpected result, I think. So we did a lot of parameter variation, just as a few examples to show you here. We have a plume of about 100 degrees hotter than the previous plume. In this case, same processes occur. It's just that they happen faster and produce more topography. So after 90,000 years, you can have a 500-meter rim. More interesting is actually if you lower the temperature or have a smaller plume. So because of that viscous dependence on the strain rate, these less buoyant things, so either a smaller initial plume or a colder initial plume, rises slower, doesn't form that viscous cap, and it actually rises straight up through. So in that case, you don't get these corona rim topographies. So melt just rises and focuses to a point. Example to show some real data. I've just been showing you schematics so far. This data is actually from Leah Sabbath. Go see her poster tonight on more about this. But as you can see, a little bit of cherry picking, but we can match topography in the model to real data. And finally, just one under Earth conditions. Similar plume or plume body. But then we have a lithosphere of 65 kilometers, crust of about 10 kilometers, trying to go for some oceanic lithosphere here. And then we have a surface temperature of 295 and using Earth's gravity. In this case, essentially just because the lithosphere is so cold, it doesn't really, it's too viscous, too strong, doesn't really support any topography. No melt really ever breaks through even after several million years. And so you just don't get a corona because of that. And again, work in progress, working on higher resolution models, 3D models. But as of what we have right now, we can recreate corona topography and fractions. This interesting strain rate dependent rheology yields lateral plume spreading against the base lithosphere, and then you can support topography with these buoyant melt-rich regions. And also, since all of these things are happening at timescales of tens of thousands of years to millions of years, if we see corona at the surface, and they're changing into different forms of corona, that may indicate corona are active at those timescales. Thank you.